Okay, I'm gonna start in a little bit, but I know I'm just trying to correct for some platform defaults that are kind of poor, because this is gonna tweet out a link to the live stream, but the X resolution, the Twitter video resolution sucks. You should join on YouTube instead for comments. Right. And this is going to be a simple one. I'm just going to try to spend some time and catch up on papers. I have a backlog of maybe like a couple dozen papers that are in here that I need to catch up on, and I figure I might as well read together. I will be checking out the comments and also playing the audio of the papers as per the commentary at the bottom. So let's get started with Mini-Gemini.
This reading is brought to you by Mars Race, Stake a Claim on the Red Planet, available on Android and iOS. Mini-Gemini, Mining the Potential of Multimodality Vision Language Models. Authored 2024 by Yanwei Li, Yuqin Zhang, Chenyao Wang, Zhisheng Zhang, Yixin Chen, Ruhang Xu, Xiaodeng Lu, Jia Jia. Abstract, asterisk operator equal contribution. 1. Introduction. With the rapid evolution in large language models, LLMs, 1 to 3, empowering the impressive capabilities for multimodality inputs is becoming an essential part of current vision language models, VLMs, reference 4, 5. To bridge the modality gap, several studies are conducted to marry vision with LLMs from images, 6 to 8 to videos, reference 9, 10. Despite these advancements, a significant gap remains between academic initiatives and the prowess of well-established models like GPT-4, reference 4, and Gemini, reference 5, which are trained with huge amounts of data and resources. For vision itself, image resolution is a core part of explicitly, despite the surrounding environment with minimal visual hallucination. To this end, more attempts are performed to further improve the visual understanding in current VLMs. For instance, LLAVA Next reference 11 and OtterHD reference 12 are proposed to enhance the ability based on previous work, reference 7, 13, by improving the image resolution. Increasing the number of visual tokens with higher resolution images undeniably enriches visual embeddings in LLMs. However, this improvement comes with escalated computational demands and associated costs, particularly when processing multiple images. Moreover, the existing data quality, model capabilities, and application scopes remain inadequate for accelerated training and development processes. This scenario prompts a critical inquiry: how to push forward the VLMs approaching well-developed models with acceptable cost in an academic setting? To answer this question, we explore the potential of VLMs from 3 strategic aspects, i.e., efficient high-resolution solution, high-quality data, and expanded applications. Firstly, we utilize ConvNet to efficiently generate higher resolution candidates, thus enhancing visual detail while maintaining the visual token count for LLMs. To bolster data quality, we amalgamate high-quality datasets from diverse public sources, ensuring a rich and varied data foundation. Furthermore, our approach integrates these enhancements with cutting-edge LLMs and generative models, aiming to elevate VLM performance and user experience. This multifaceted strategy enables us to delve deeper into the capabilities of VLMs, achieving significant advancements within manageable resource constraints. In general, our method employs an any-to-any paradigm, which is adept at handling both image and text as input and output. In particular, we introduce an efficient visual token enhancement pipeline for input images, featuring a dual encoder system. It comprises twin encoders, one for high-resolution images and the other for low-resolution visual embedding, mirroring the cooperative functionality of the Gemini constellation. During inference, they work in an attention mechanism, where the low-resolution one generates visual queries, and the high-resolution counterpart provides candidate keys and values for reference. To augment the data quality, we collect and produce more data based on public resources, including high-quality responses, reference 14, 15, task-oriented instructions, 16 to 19, and generation-related data, reference 20, 21.
Hey, Jim.
The amount and quality improve.
Glad you caught this one. I know the timing's always weird. If I was trying to be a regular YouTuber, I should have a regular time, but my life doesn't afford that right now. Yeah, about to celebrate my birthday and figure I had some time and wanted to calm down from a very busy day. So I am passing it by doing some paper reading, which I need to do anyway, keeping myself accountable, and sharing with you guys. So thanks, Jim. And what is the speaker of your wake hours between research, commercial work, and personal life? I don't know. Yeah, sorry. I mean, I try to work a good 9 to 5, and sometimes I work more, sometimes I work less. All right, let's keep going. Comments continue to be welcome.
Increase the amount and quality, improve the overall performance, and extend the capability of model. Additionally, our model supports concurrent image and text generation, facilitated by the seamless integration of our VLM with advanced generative models, reference 22. It leverages VLM guidance for image generation by providing the generated text from LLMs. The Mini-Gemini framework can be easily instantiated with a range of LLMs from 2B to 34B parameter scales, as detailed elaborated in section 3. Extensive empirical studies are conducted in Section 4 to reveal the effectiveness of the proposed method. Remarkably, our approach attains leading performance in various settings and even surpasses the well-developed Gemini Pro, reference 5, QuinVL+, reference 23, and GPT-4V, reference 4, in the complex MMB, reference 24, and MMU, reference 25 dataset, respectively. These results underscore Mini-Gemini's potential to set new benchmarks in the realm of VLMs, highlighting its advanced capabilities in handling complex multimodal tasks. 2. Related work. Large language models. Recent progress in natural language processing, NLP, has been dramatically accelerated by advancements in large language models, LLMs. The seminal introduction of the Transformer framework, reference 26, served as a cornerstone, enabling a new wave of language models such as BERT, reference 27, and NOT, reference 2, that exhibit profound linguistic understanding. The inception of the generative pre-trained transformer, GPT, reference 28, introduced a novel paradigm through auto-regressive language modeling, establishing a robust method for language prediction and generation. The emergence of models like ChatGPT, reference 1, GPT-4, reference 4, Llama, reference 3, and Mixtral,
So they're just doing a lot of blah, blah, blah for like referencing other language model developments, none of which is surprising. Figure 2 seems to be the relevant paper or section here, describing an any-to-any workflow with a high-resolution vision encoder and a low-resolution one. This dual vision is why they call it Gemini. It's got nothing to do with the Google paper, the Google model. They have feature maps with a windowed implementation for the high resolution, and for the low resolution they have visual embeddings, and these are the queries, and that's the keys and values. That's interesting. And doing cross attention on that to get mine tokens combined with text input. This part is not controversial, but it's nice to see as a diagram. Hey Vibu. And then it outputs text, and then this is a fun one. Sometimes it feeds into SDXL for output image. Just for fun, I guess. I don't believe this works, but maybe there are some examples down below.
And Mixtral, reference 29, further exemplify the field's rapid evolution, each demonstrating enhanced performance on complex language pro. Vision language models, the convergence of
I'm skipping ahead because I don't
vision tasks,
like this
showcasing
stuff.
the feasibility of cross-modal applications. Recent developments underscore a growing trend toward leveraging the robust capabilities of LLMs within the realm of VLMs. Innovations like
Yeah, I've covered all this stuff before, so this is boring.
Different from them, we aim to explore the potential for both comprehension and generation. LLM as
this one is new.
Combining LLMs with image outputs has emerged as a pivotal area in recent multimodal research. Methods like InternLMX Composer, reference 44, 45, utilize image retrieval to produce interleaved text and image outputs, bypassing direct generation. Conversely, auto-regressive token prediction approaches, exemplified by EMU, reference 46, 47, and SEED, reference 48, 49, enable LLMs to decode images through massive image text data directly. These methods require enormous training resources, and their auto-regressive nature leads to undesirable latency. Recent studies 50 to 52 strive to align with latent diffusion models, reference 22, to streamline image generation. They typically require designing text embeddings and additional optimization to achieve the desired generation effect. This joint training can compromise the performance of VLMs in text generation. Mini-Gemini distinguishes itself by adopting a text data-driven approach to enable the model to generate high-quality images. We leverage a mere 13K pure text data to activate the LLM's ability as a high-quality recaptioner, reference 53, without undermining the fundamental performance of VLMs. 3. Mini-Gemini.
Vib was asking, what is this audio? Is something reading this paper out loud or something? Yes, as per the thing at the bottom, which is supposed to be scrolling and telling you what I'm doing, there is a podcast called papersread.ai, which auto generates or reads out the papers in audio format. And I just use it as an accountability tool to read through papers. But also, whoever is making this, someone called Rob, and that's all I know. Oh, Rob Al Johnson. Oh, this is not a real person. 14 people subscribe to this thing, but the way the papers that they choose tend to have pretty high signal. I don't know how they choose these things. I would really love to figure out how they choose these things because it's unusual. But I'll mostly give it a scan if it is in a region, if it's in a domain I care about. What paper is this? We're covering the Gemini paper, Mini-Gemini paper. I put the link up here, and the URL should be visible here. I was also checking out, it references the InternLMX Composer model, so I was just trying to figure out what that one was. It looks like there's a demo here. Wow, this is a good demo. Okay, cool. Yeah, I don't know how seriously I should take this, but it seems a pretty interesting model. I guess the paper would have more details. Why are the papers so hard to find? This one. Give me an arch diagram, arch. No arch diagram. No arch diagram, just a bunch of demos. Yeah, whatever. Okay, I don't care enough to continue, so I'm just going to go back up to cover the Mini-Gemini framework. Let's keep going.
Mini-Gemini. The framework of Mini-Gemini is conceptually simple. Dual vision encoders are utilized to provide low-resolution visual embedding and high-resolution candidates. Patch info mining is proposed to conduct patch-level mining between high-resolution regions and low-resolution visual queries. LLM is utilized to marry text with images for both comprehension and generation at the same time. 3.1 dual vision encoders in the Mini-Gemini framework.
All right, let's take a pause to check out this image. Details and patch info mining. They have the high-resolution feature map and the low-resolution visual embedding. One of them feeds to the queries and the other feeds to the Ks and Vs. I don't know if that's like the most. So I guess this is the context and this is the embed. It almost feels like it should be the other way around. I'm not sure why they're doing it. They're making the queries the embeddings. It's not really explained at all. Second, details and visual token extension. There's the image splits and a raw image. I don't understand this at all.
In the Mini-Gemini framework, both text and image inputs can be processed with the option to handle them individually or in combination. For illustrative clarity, we consider the concurrent processing of both modalities. As depicted in Figure 2, the processing begins with a high-resolution image XH element of RH times W times 3, from which a corresponding low-resolution image XL element of RH times W times 3 is generated via bilinear interpolation, ensuring H is less than or equal to H. Then, we process them and encode into multi-grid visual embeddings in two parallel image flows. In particular, for the low-resolution LR flow, we maintain the traditional pipeline, reference 42.7, and employ a clip pre-trained bit, reference 40, to encode the visual embedding XL element of Rn times C, where n denotes the number of visual patches. In this way, the long-range relation among n visual patches can be well preserved for subsequent interaction in LLMs. As for the high-resolution hour flow, we adopt the CNN-based encoder for adaptive and efficient HR image processing. For instance, to align with the LR visual embedding, the LAION pre-trained reference 54, convenext reference 55 is used to serve as an HR vision encoder. Therefore, we can obtain the HR feature map XH element of Rn times n times C by upsampling and concatenating the features from different convolutional stages to 1/4 input scale. Here, n equals H 4 times with 4 equals n times M2 denotes the number of HR features, where M reflects the pixel-wise feature count within each HR segment, as illustrated in Figure 2. 3.2. Patch info mining. With the above generated LR embedding XL and HR feature XH, we propose patch info mining to extend the potential of VLMs with enhanced visual tokens. In particular, to maintain the number of final visual tokens for efficiency in LLMs, we take the low-resolution visual embedding XL as query Q element of Rn times C, aiming to retrieve relevant visual cues from HR candidate. Meanwhile, the hour feature map XH is taken as key K element of Rn times M2 times C and value V element of Rn times M2 times C, as depicted in Figure 2. Here, the low-resolution patch in Q correlates with the corresponding high-resolution subregion in K and V, encompassing M2 pixel-wise features. Therefore, the patch info mining process can be formulated as TV equals MLP Q plus softmax phi Q times phi K T times phi V1, where phi and MLP indicate a projection layer and a multi-layer perceptron, respectively. As presented in Figure 3a, this formula encapsulates the process of synthesizing and refining the visual cues, leading to generation of enhanced visual tokens TV for subsequent LLM processing. It ensures that the mining for each query is confined to its corresponding subregion in XH with M2 features, thus preserving efficiency. This design allows for the extraction of HR details without expanding the visual token count of TV, maintaining a balance between richness of detail and computational feasibility. Furthermore, visual token extension is also supported in the design patch info mining. As depicted in Figure 3b, we can extend the visual token to 5n to capture more details. This is achieved by incorporating the original image along with its 2 times upscaled counterpart, resulting in a batched input XL element of R5 times H times W times 3. And we can get the encoded visual embedding XL element of R5 times N times C with the LR Vision encoder, as detailed in section 3.1. Thanks to the flexible design of CNN-based HR Vision encoder, it can adeptly handle the augmented visual token count during the patch info mining. The only difference in the aforementioned procedure is the subregion in XH should be changed according to the expanded visual embedding XL. We can also upsample the HR input to better support the higher resolution if needed, as experimentally analyzed in Table 2. 3.3 Text and image generation. With the mined visual tokens TV and input text tokens TT, we concatenate them as the input to LLMs for autoregressive generation, as presented in Figure 2. Distinguished from traditional VLMs, reference 42, 43, 11, the proposed Mini-Gemini supports both text-only and text-image generation as input and output, i.e. any-to-any inference. Despite the image comprehension, we anchor Mini-Gemini's ability to generate images on its outstanding image text understanding and reasoning capabilities. Unlike recent works 50 to 52, 47, which address the domain gap between text embeddings of LLMs and generation models, we choose to optimize optimize the gap in the domain of language prompts. Precisely, Mini-Gemini translates user instructions into high-quality prompts that produce context-relevant images in latent diffusion models, reference 2256. This approach is reflected in subsequent high-quality image generation frameworks, such as DALL-E 3, reference 53, and Zora, reference 57, which leverage the generation and understanding capabilities of VLMs to obtain higher quality text conditions for generation tasks.
Yeah, so, I think this is obviously correct. The ability to pipe in visual tokens to better improve generation looks like an optional thing here. I kind of make fun of it, but actually it's going to generate better images for sure because it can mine tokens like that. Yeah, I know the voice is weird. It's mostly for me. I'll pause it and comment like I'm doing now, and you should be able to hear me well because I have my good mic here. This is the good mic. It's a Shure something. I don't know what the hell it is. It's the one that's affordable on Amazon. That doesn't suck. And I'm just kind of reading through. We're reading together. You can read along. You can see what page I'm on. And if that's useful to you, great. If it's not, you have other things that you can entertain yourself with, but also I'll stop to answer questions. Jim says, do I regret transition from front-end React and frameworks to AI? Absolutely not. Front-end is stuck in a complete rut. I don't know if front-end people realize, but it's extremely boring, and there's no advance that is relevant beyond like the server component stuff, most of which is very navel-gazy and not useful. So yeah, it's way more interesting, and I do think that a lot of value is created. There is a lot of hype and fluff, and I'm partially responsible for that. But I think there is a lot of real value, and I think a lot of people are better off exploring and building with AI. Cool. I can keep going. I'm 5 pages into this paper. I think it's the decent paper so far. Doesn't really trip any of my warnings, which is generally tend to be good because like there's a lot of very bad papers out there. So I like what I read so far. Don't know what I think about this sort of the real novel contribution is this patch info mining. Like these 3 paragraphs is effectively like the core idea. Everything else is like kind of you've seen those versions of these things before. And then I think now it's about to discuss data set and model. These are not really going to be super useful for now, unless you're trying to repo this thing. Okay.
Obtain higher quality text conditions for generation tasks. Cybersecurity is known for better cross-modality alignment and instruction fine-tuning. We collect high-quality data sets from publicly available sources. In particular, for cross-modality alignment, we utilize 558K image caption pairs from the LL100KQA pair, reference 17, 4K chart QA, reference 18, 10KB. The training data encompasses 2 tasks. Is suitable for the conversation context, bringing 5K instructions in total. For both kinds of data, in each query to GPT-4, we randomly sample 5 high-quality SDT4 experiments. In this section, we first outline our experimental framework, commencing with the experimental setup. Subsequently, we compare Mini-Gemini with leading methods on various benchmarks. Component-wise analysis and qualitative results are given at the end of this section. 4.1. Experimental setup. Implementation details. In this study, we instantiate Mini-Gemini with the Clip pre-trained VTL, reference 40, for LR Vision Encoder and the LAION pre-trained Convene XL, reference 54, for HR Vision Encoder. For efficient training, we keep 2 vision encoders fixed and optimize the projectors of patch info mining in all stages. Meanwhile, we optimize the LLM during the instruction tuning stage only. Regarding the training scheme, we optimize all the models for one epoch with the AtomW optimizer and a cosine learning schedule. In most cases, the initial learning rates for modality alignment and instruction tuning are respectively set at 1E-3 and 2E-5, with an adjusted rate of 1E-5 for the MIXTRAL 8x7B and Hermes 2E34B to ensure stable instruction tuning. The framework involves training on 8x800 GPS for standard machine configurations. For the largest model with Hermes 2E34B, we leverage 4 machines and complete the optimization within 2 days with DeepSpeed 03 strategy. For the HD version, the total cost is enlarged to about 4 days because of the extended visual tokens in LLMs. Datasets. For model optimization, we construct high-quality data for cross-modality understanding and generation. It mainly includes 1.2M caption pairs for modality alignment and 1.5M single or multi-round conversations for instruction tuning, as elaborated in section 3.3. Moreover, we report results on widely adopted zero-shot image-based benchmarks, including VQAT, text VQA, reference 67, MMB, MM-Bench, reference 24, E, reference 68, Embed, reference 60.
I'll make a comment about this 8 by A800 GPUs using 4 machines and completing the optimization within 2 days, maybe about 4 days. I think most people don't understand how cheap it is to make models multimodal. This is very, very slightly more expensive than Lava, but not very much so. And for the increased accuracy you get with a dual vision encoder thing, I think this is probably way better. It's a good idea. This is basically Lava 2. I'm sure the Lava guy, Hao Tian, would disagree with that, but it's a good advancement. It's great that it's so cheap. Every model should be multimodal this way. Let's keep going.
Event reference 69, MMMU reference 25, and Map Vista reference 70 dataset.
Yeah, there's a question here from YouTube about, is that your own Whisper TTS skip tables? Yes, it did skip tables. That is papersread.ai, which is just helping me, accompany me while I read, so it's not completely dead air.
Datasets 4.2 main results, normal resolution. In table 1, we compare with previous leading approaches across several settings, including normal and high resolution, and also consider private models. At normal resolution, Mini-Gemini consistently outperforms existing models across a wide range of LLMs. In the efficient model category, Mini-Gemini, when configured with Gemma 2B, reference 36, demonstrates superior performance. High resolution. To validate the framework for extended visual tokens, we perform experiments with an input size of 672 for LR visual encoder and 1536 for HR visual encoder in table 1. As discussed above, the hour visual encoder primarily serves to offer high resolution candidate information. Importantly, despite the increased resolution, the effective number of visual tokens processed by the LLM remains consistent with the LR input size of 672, ensuring computational efficiency. The benefits of this approach are particularly evident in detail-oriented tasks. For example, in the text VQA, reference 67, benchmark, our method achieved a performance rate of 74.1% with the Hermes 2E34B configuration, closely matching the performance of the well-established Gemini Pro, reference 5. Detailed results in Table 1 show that Mini-Gemini excels in more challenging benchmarks as well. For instance, the proposed method is on par with QuenVL+, reference 23, on the Math Vista, reference 70, and MMMU, reference 25, benchmark, and even surpasses Gemini Pro and GPT-4B on the widely adopted MMV, reference 24, benchmark. 4.3 component-wise analysis, patch.
Gautam says it uses DP03 but not PyTorch FSDP, which is very similar. Sometimes it could just be familiarity with tool sets, especially if they've done previous papers also using a code base that use that stuff already. That's all I got for you.
Patch info mining. We first delved into the proposed patch info mining and report results in Table 2.
I noticed some delving in this paper. Delve is mentioned 3 times. Yeah. Little sus.
Report results in Table 2. It is clear that the model achieves significant gains with the ConveNextL integrated as the vision encoder for HR images. For example, when the LR and HR are respectively set to 224 and 512, the model increases 4.0% and 18.1 in text VQA and ME datasets. Elevating the HR resolution to 768 further widens the performance margin, achieving a 5.7% uplift in text VQA compared to the baseline. These results underscore the substantial impact of patch info mining in harnessing more detailed visual cues. When we further extend the LR resolution to 336, patch info mining still contributes consistent gains. For instance, with the default ConveNextL as vision encoder, it surpasses the baseline with 3.3%, 6.3, and 3.5% in text VQA, reference 67, ME, reference 68, and embed, reference 69 dataset, respectively. This proves the capability of design modules with input resolution scaled up. Vision encoder. To investigate the effect brought by mining candidates, we conduct experiments with various HR vision encoders in Table 2. Compared with the default ConveNextL, we add 2 encoders for contrast trials, i.e. ConveNextB and ConveNextXXL. With the basic ConveNextB, the model performs better in text VQA, reference 67, and embed, reference 69. However, the ConveNextL encoder consistently delivers peak results, especially in the ME and embed datasets, indicating a superior balance in handling detailed visual information. We can conclude from the table that a larger vision encoder for HR images contributes more to the candidate quality, but the model converges with a too large encoder like ConveNextXXL. Hence, considering the balance between effectiveness and computational efficiency, ConveNextL is chosen as the default HR vision encoder. This decision is based on its ability to provide high-quality visual information mining while maintaining reasonable computational demands, as evidenced by the comparative performance across the benchmarks. High-quality data. In this era, the significance of high-quality data for enhancing the capabilities of LLMs and VLMs cannot be overstated. In our comprehensive analysis of data combination effects presented in Table 3, we begin with a baseline model incorporating patch info mining. The integration of high-quality captions from shared GPT-4 volts reference 14 yields improved visual alignment and performance gains. We validate the zero-shot performance on the text VQA reference 67 benchmark, notably removing text caps reference 59 data from the training set in line with previous studies reference 11. This modification led to a notable performance decrease, underscoring the value of specific data types in training. To counteract this decline, we incorporate additional high-quality captions from LAION GPT-4b, reference 60, and OCR-specific data, thus enhancing the model's OCR reasoning capabilities. More details are provided in the appendix. As elaborated in section 3.3, we utilize generation-related instructions to expand the application. It is interesting to find that such data also benefits the image understanding ability and brings 3.3% gains in embed dataset. Moreover, with a high-quality GPT-4b responses from RLAP reference 15 dataset, the framework respectively pushes the baseline over 7% and 9% in text VQA and embed datasets. This comprehensive evaluation underscores the pivotal role of strategic high-quality data integration in amplifying the potential of the Mini-Gemini framework. Visual token extension. As depicted in Figure 3b, the proposed patch info mining is adeptly designed to accommodate extended visual tokens, thereby generalizing its utility across different input resolutions. We validate the effectiveness of the token extension in Table 3. When increasing LR and HR input resolution, the model achieves significant gain in all benchmarks. Notably, in detail-oriented tasks such as text VQA, we observe a performance uplift of over 3%, indicating a significant enhancement in the model's ability to handle complex visual data. Our empirical observations suggest that the increase in resolution significantly diminishes visual hallucinations, leading to more accurate and reliable image comprehension. Generally, with the increased visual token number, Mini-Gemini can be scaled up towards better capability. We can also draw the same conclusion from high-resolution results in Table 1. 4.4. Qualitative results. Visual understanding. To ascertain the visual comprehension prowess of Mini-Gemini in real-world settings, we apply it to a variety of understanding and reasoning tasks in Figure 5. Thanks to the patch info mining and high-quality data, Mini-Gemini can well solve several complex cases. For example, it is capable of recognizing plotted curves in graphical data and directly translating them into Python code for immediate application.
Ooh, that's cool.
Beyond mere recognition, it exhibits a keen attention to detail, accurately describing intricate elements within complex indoor scenes and demonstrating a nuanced understanding of character associations and memes. Moreover,
I gotta see that. That's freaking cool.
Moreover, Mini-Gemini's analytical capabilities extend to chart analysis and practical problem solving, such as intelligence tests. Image generation. In Figure 6, we provide a comprehensive evaluation of Mini-Gemini's generation capabilities. Compared with recent studies such as AnyGPT, reference 52, and Chatillusion, reference 51, our stronger multimodal understanding ability allows us to generate text-to-image captions that better align with the given instructions, resulting in more contextually appropriate image text answers. A noteworthy point, as shown in Figures 1 and 6, is its proficiency in generating high-quality content based on multimodal human instructions with text-only training data. This capability underscores Mini-Gemini's robust image text alignment and semantic interpretation skills, which come into play effectively in the inference stage. By leveraging the powerful reasoning ability of the LLM, it can produce reasonable image text outputs in single or multi-round conversations, reproduced with
that's the stuff that I was talking about earlier. That's pretty cool. Generate matplotlib code for resulting qualities and self-function. It read the numbers correctly in here, mu and sigma in there. What else can we observe? The axes are a little off, but not by much. Here's exactly correct. Describe the image in detail. It's a good description. Can you explain this meme? I love the gym. Where are you at the gym? Cool. At the send me page. McDonald's. Wow, this McDonald's thing is great. All right, I want to test this. So let's go here. Let's grab this. I love how I can casually use GPT Vision, even though this time last year it was not available. GPT Vision doesn't know about McDonald's. Why is the M different? And what could it be? So yeah, I think this might have beat the ChatGPT because it doesn't know about McDonald's. Yeah, that's a decent answer though. All right, what's the last one? Spot 2 data points to stand out in these charts. Oh boy. All right, let's give that here. Let's put it here. Okay, and then let's do this, that, put that in here. All right. So here it says annoying pain and furnished cages. Oh, annoying pain in battery cages and in furnished cases. So if you highlight here, here's a detail well organized markdown table comparing all the data. Okay, cool. Here I picked up annoying pain versus hurtful pain. Cool. All right. The pain level stuff is here. Ooh. 420, 253, 27, 003, 384, 197, 10, 003, 130, 109, 10, 003. So perfect replication of the table. And yeah, really cool. Radu Georgiou says, GPT vision is so bad right now. I tried to give you a simple image with some text in the table, and it couldn't extract anything. It gave me tons of excuses. I can't run it. OCR code, blah, blah, blah. Yeah, don't pay for GPT-4. Enough said. Cool. Tell me a story about a fire-spitting dragon killed by a man. It generates an image for you. Yeah. Okay. Yeah, I don't know how much this image generation stuff is. Huh. Generate an image of a spider and riding a motor bike. I wonder if ChatGPT knows Spider-Man. This guy clearly knows Spider-Man. Okay, cool. Conclusion and discussion.
Reproduced with generated code import matplotlib. Pyplot is PLT import numpy. Y2 equals 1 NP. SQRT 2. After the modern kitchen interior, the kitchen features a white cabinetry with a wooden countertop and a central island.
Wow. I mean, it's pretty close to Spider-Man with the blue and the red, but not exactly Spider-Man. I think they might have passed the copyright check because this is very not Spider-Man, but has elements of Spider-Man. Okay.
Countertop and a central island with a white tabletop. The island is surrounded by 4 green velvet chairs with black legs. On the countertop, there are various kitchen items, including a coffee, particularly noteworthy due to its higher values. Excruciating pain.
So,
hurtful pain.
Okay, yeah, we've reached the end at this point. It's just kind of more and more demos. Did they release the model? Model's here. Yeah, it looks legit. Excellent. They released a bunch of sizes of model. Ooh, shit. They provide data set. Oh. Wow, this is going to be tough to run. Okay. Interesting. Great work. Yep, this is work built on lava. Okay. Yeah. What is DV Lab? What is that? DVision Lab. Okay. dvlab.ai. It is a Chinese institution. 10 papers accepted at CVPR. Members. Fuck that. This is it's Chinese. Super Chinese. HKUST. Oh, these are Hong Kong things. Okay. All right, that's all I care about. Let's go on to the next thing and the next thing and the next thing and the next thing. Okay, so maybe I'll do like 2 more papers and then we're good. So next we're going to check out something else.
Exclusion and development process in the past decades. Automated.
Someone's suggesting AutoCodeRover, or this thing's suggesting AutoCodeRover. I kind of want to do ReFT. I feel like AutoCodeRover won't be that interesting. I may eat my words. So given that it's a Singapore paper, I have to cover it. So let's see if we can cover it. Okay, I will pin the next paper onto the comments in here. Nope, that's not it. Never mind. That's where's the AutoCodeRover paper? AutoCodeRover. Here we go. All right, Vibu says he's up for ReFT. So maybe we'll just do the AutoCodeRover real quick. And then we'll do ReFT, and then we'll call it a night. So let's do AutoCodeRover. Wow, this is a 1 hour long paper.
For issue summarization, bug reproduction, fault localization, and program repair have been built to ease the work.
Why is this an hour long paper when this thing's like 12 pages? That makes no sense. Oh, but this is like very single spaced. Okay. Cool. I am not looking forward to this paper. But because of NUS, I have to read it.
Have been built to ease the workload of developers. Recent progress in large language models, LLMs, has significantly impacted the development process, where developers can use LLM-based programming, ultimately leading to a program modification or patch. In contrast to recent LLM agent approaches from AI researchers and practitioners, our outlook is more software engineering oriented. We work on a program representation, abstract syntax tree, as opposed to viewing the software project as a mere collection of files. Our code search exploits the program structure in the form of classes, methods to enhance LLM's understanding of the issue's root cause and effectively retrieve the context via iterative search. The use of spectrum-based fault localization using tests further sharpens the context, as long as a test suite is available. We consider the recently proposed SWE Bench Lite, which consists of 300 real-life GitHub issues involving bug fixing and feature additions. Experiments on SWE Bench Lite show increased efficacy in solving issues on SWE Bench Lite as compared to recent efforts from the AI community. Interestingly, our approach resolved 67 GitHub issues in less than 10 minutes each, whereas developers spent more than 2.77 days on average. We posit that our workflow enables autonomous software engineering, where, in future, auto-generated code from LLMs can be autonomously improved. CCS concepts, software and its engineering right-pointing arrow automatic programming, software testing and debugging, computing methodologies right-pointing arrow natural language processing. One beyond automatic programming, automating software engineering tasks has long been a vision among software engineering researchers and practitioners. One of the key challenges has been...
I'm going to skip ahead to all the blah, blah. I'm going to skip ahead to what we actually do here, which is like a half a page later.
Holds significant promise in given this motivation of automating program repair and the better understanding of particular GitHub issues by exploiting the program structure. Technically, our solution works as follows. Given a real-life GitHub issue, LLM first analyzes the attached natural language description to extract keywords that may represent files, classes, methods, code snippets in the codebase. Once these keywords are identified, we employ a stratified strategy for the LLM agent to retrieve code context by invoking multiple necessary code search APIs at one time with the keyword combinations as arguments, e.g., search underscore method underscore and underscore file. These code search APIs are running locally based on AST analysis and are responsible for retrieving code context such as class signatures and method implementation details from a particular location in the codebase. By collecting the project context with code search APIs, LLM refines its understanding of the issue based on the currently available context. Note that our code context retrieval will proceed in an iterative fashion. The LLM agent directs the navigation and decides which code search APIs to use, i.e. where, what to retrieve code. In each iteration, based on the current available context returned from the previous API calls, AutoCodeRover then inquires whether there is sufficient project context and subsequently uses the collected context to derive the buggy locations. The patch construction is then handled by another LLM agent, which considers the buggy locations as well as all the context collected so far for those locations.
I wish they had a diagram showing what they just described here. Maybe here is the part of it. Maybe, yeah, this is actually what I want. So let's consider this. Problem statement. Then you collect context by invoking APIs, API invocations, results of invocations, puts it into context analysis. Is it sufficient? No. Is it yes? And then buggy locations, code at buggy location, please write patch, blah, blah, blah. And patch generation, patch cannot be applied to program, please try again. Apply yes, there's a loop here, and yes, final patch. And AutoCodeRover patch looks like this. Developer patch looks like that. It looks very close. It looks very close, but minor differences. Yeah, no big deal.
collected so far for those locations. AutoCodeRover also can leverage popular debugging techniques such as spectrum-based fault localization (SVFL), reference 35, to decide more precise code search APIs for context retrieval if a test suite accompanying the project is available. SVFL primarily considers the control flow of the passing and failing tests and assigns a suspiciousness score to the different methods of the program. The LLM agent may prioritize retrieving context from particular methods and classes if the fault localization result is provided, e.g., when a method appears both in the issue description and in the output of fault localization. In the last step, AutoCodeRover may perform patch validation, a test suite available, to determine whether the patch produced by AutoCodeRover passes the test in the given test suite. Otherwise,
I feel like this method appears in both issue description and output of fault localization. Okay, yeah, that's not that bad, but like you are risking in training to the test here by doing this stuff like this.
Otherwise, AutoCodeRover will rerun the patch generation with a retry threshold until a correct patch is found. We see the need to endow a software engineering-oriented outlook to the recent flurry of activity on LLM agents for software engineering, which mostly has only an AI flavor. We believe that the software engineering angle can be conveyed via 4 dimensions and can enhance the capabilities of LLM agents. We work on program representations, abstract syntax tree, or AST, as opposed to viewing the software project as a collection of files. We posit that working on program representations like AST will be critical to autonomous software engineering workflows. To solve GitHub issues, we focus on code search in a way that resembles the activity of a human software engineer. So we try to use the program structure classes, methods, code snippets in searching for relevant code context. This leads to a more effective usage of the context provided to LLM. We posit that higher efficacy of automated repair is more important than time efficiency, as long as the time is within a threshold. It is well known in empirical software engineering research that time limits of 30 to 60 minutes for automated repair are tolerable, based on extensive developer surveys in the field, reference 23. We thus set a modest time limit of 10 minutes and report 22% efficacy on SWE bench Lite in solving GitHub issues. We can compare this time limit of 10 minutes to the average time of 2.77 days to fix the GitHub issues manually. Finally, one should be able to exploit debugging analysis techniques like test-based fault localization to guide the search for code in resolving GitHub issues. We show that use of fault localization in setting the code context leads to an increase in efficacy from 16% to 20% in a single run of AutoCodeRover on SWE bench Lite environments, which may involve autonomous improvement of automatically generated code. 2. Background 2.1. Program repair. Test suite-based automated program repair, APR, has attracted significant attention in the last decade, reference 9. These techniques aim to generate a patch for a buggy program to pass a given test suite. APR techniques typically include search-based, semantic-based, and pattern learning-based APR. Search-based APR techniques like GenProg, reference 33, take a buggy program and generate patches using predefined code mutation operators, or search for a patch over the patch states that passes the given test suite. Semantics-based APR techniques, reference 21, 22, generate patches by formulating a repair constraint that needs to be satisfied based on a given test suite specification, and then solving the repair constraint to generate.
Sergio says, makes sense to me. I've seen it makes a difference with GraphQL using the SE instead of just text. Yep, lots of people are trying this.
Constraint to generate patches. Learning-based APR techniques, reference 19, 30, 39, often train a deep learning model with large code repositories and are guided by a specific representation of code syntax and semantics to predict the next tokens that are most likely to be correct patch. Recent work, reference 7, 11, 37, has shown use of LLMs for automated program repair. This line of work often assumes the buggy program statements are given, i.e. perfect fault localization assumption, and focuses on constructing a PR-specific prompts that guide LLM to generate a patch for the selected buggy program statements multiple times until a patch that passes all tests is found. However, obtaining buggy locations for a large project is an essential and challenging task in resolving real-life bug reports. APR techniques have been successfully deployed in industries for domain-specific bug fixing, reference 3, 20, 34. However, a long-standing challenge for the APR techniques is to resolve general real-life software issues from scratch. The above APR techniques rely on a high-quality test suite, which is not always available in the real world, and they do not leverage the valuable natural language specification from the original problem description. To address these challenges and achieve autonomous software engineering, we focus on resolving GitHub issues from a real-life dataset. 2.2. Dataset, SWE bench, reference 13, is a benchmark that aims to evaluate the capabilities of large language models in resolving end-to-end real-life software engineering tasks. The benchmark consists of 2,294 real-life software engineering task instances collected from the repositories of 12 popular large Python projects, e.g., Django, Symfony. Each SWE bench task instance contains a pair of GitHub issue and corresponding pull requests. The GitHub issue either reports a bug to be fixed or requests to implement new features. The pull request includes the code changes made by human developers to resolve the issue and test cases that prevent the issue. Unlike traditional code generation tasks in human eval, reference 6, and MVPP, reference 18, benchmark, resolving a SWE bench instance is particularly challenging because it requires automatically generating code changes that address the problem in a GitHub issue from a matured large code repository based only on the issue description. More specifically, the process may involve a series of complex tasks like reasoning the target bug location across files in the code repository, analyzing the root cause of the issue, proposing bug fixing strategies, and eventually writing a patch that passes all the test cases added in the pull request. SWE bench team also constructed a light version of SWE bench Lite, due to the high cost of evaluating in the complete SWE bench. SWE bench Lite includes 300 task instances sampled from SWE bench, following a similar GitHub issue repository distribution as SWE bench. SWE bench Lite removed task instances with meta files such as images, external links, and instances without proper description, e.g., short problem statement fewer than 40 words. In the following sections, we describe our design of an AI program improvement framework for handling real-life software issues and demonstrate its effectiveness in SWE bench Lite. 3. Motivating example. In this section, we illustrate.
Paul Tan says, sounds unfair. They can keep trying until it passes the test suite. Yeah, I have bad news for you for the state of AI research. This is normal.
We illustrate how our tool AutoCodeRover can collect code context and generate a patch from an issue description in the corresponding project codebase. We show an example of a challenging feature addition task. Figure 1 demonstrates the workflow of AutoCodeRover on an issue submitted to the Django issue tracker 2. This issue is classified as new feature in the issue tracker and is included in SWE bench light with the Django 13933. The first part of figure 1 shows the issue description. The code part is simplified for brevity. This issue requests adding support to the model choice field class so that it shows the value of the invalid choice when raising a validation error. With this issue description, AutoCodeRover operates in 2 stages: context retrieval, step 1 to 3 in figure 1, and patch generation, step 4. First, a context retrieval LLM agent is instructed to collect the relevant code context related to this issue from a local copy of the Django project codebase. This retrieval is achieved by inferring relevant names, e.g. model choice field, and searching for them in the abstract syntax tree, AST, of the project. A set of retrieval APIs are provided to the agent. In step 1, the agent identifies the class's model choice field and model multiple choice field might be relevant based on the issue description, and infers that a clean method might be also of interest for validation-related issues. It then invokes the search underscore class and search underscore method underscore and underscore class APIs to retrieve more information about them. In step 2, API invocations return the signature of the classes and implementation of the method is found. Results of invocation number 3 reveals the absence of method clean in the class model choice field, which helps to refine the agent's understanding from step 1. The return class signature from invocation number 1 also reveals 2 more relevant methods to underscore Python and validate, which were not mentioned. 3. In the issue description, this suggests the retrieval should be performed iteratively in multiple steps, so that results from a previous search can become arguments of the following search. In this example, the agent then iteratively invokes search underscore method underscore and underscore class on the 2 newly revealed methods. Furthermore, by referencing results from multiple invocations, the agent can infer that model multiple choice field incorporates the invalid value into the message with %value s, and methods in model choice field can be modified similarly to model multiple choice field. In step 3, the agent receives the implementation of validate and to underscore Python methods. Among the 2 methods, it selects to underscore Python to be the more suitable place to make changes, since to underscore Python raises the relevant exception and does not include the invalid value. At this point, the retrieval agent deems the collected code context as sufficient for understanding the issue and drafting a patch. The identified buggy location, together with the gathered context and analysis so far, is passed to another patch generation agent. This agent is instructed to write patches following a specified format. In step 4, a patch is written to allow a value to be integrated into the error message by utilizing % formatting in Python. Although written in a different way compared to the developer patch, this patch achieves similar effect and passes the developer-provided test suite for this issue. 4i Program Improvement Framework. In this section, we discuss the design of AutoCodeRover. AutoCodeRover is a system incorporating AI agents for program improvement tasks in large software projects. AutoCodeRover is designed to work in a realistic software development lifecycle, in which users submit issue reports to a software repository describing
Marketing.
the workflow of AutoCodeRover as shown in figure 2. AutoCodeRover takes in as input a problem statement P of the issue to be resolved, and a codebase C of the corresponding software project. This problem statement P contains the title and description of the issue, as shown in section 3. From a problem statement written in natural language, AutoCodeRover analyzes the requirement from it and proceeds in 2 main stages, which are context retrieval and patch generation. In the context retrieval stage, AutoCodeRover employs an LLM agent to navigate through a potentially large codebase C and extract the relevant code snippets relevant to P. This navigation is enabled by a set of context retrieval APIs, section 4.2, which enables an LLM to retrieve information about the project, e.g. class signatures, and actual code snippets, e.g. method implementations. The context retrieval agent directs this navigation and decides which retrieval APIs to use based on the current available context. In order to make the LLM directed navigation more controlled, we devise a stratified state GUI invoking the retrieval APIs, section 4.3. This stratified strategy instructs the LLM to only invoke necessary retrieval APIs based on the available information and iteratively changes the set of retrieval APIs used when more code-related contexts are returned from the previous API calls. Once the context retrieval agent has gathered sufficient context about the issue, AutoCodeRover proceeds to the patch generation stage, section 4.5. In this stage, AutoCodeRover employs another LLM agent to extract more precise code snippets from the retrieved context and craft a patch based on the extracted code snippets. This patch generation agent is instructed to craft a patch in a specific 4 issue SYMPY12481 permutation constructor fails with non-disjoint cycles format, and if the produced patch does not follow the format specification or cannot be applied to the original codebase, the agent enters a retry loop, which terminates after a pre-configured number of attempts. Finally, AutoCodeRover outputs a patch that attempts to resolve the original issue. We note that the workflow of AutoCodeRover discussed so far only requires the problem statement P and codebase C as input, and do not require any program specifications such as test cases. However, when test cases are available, e.g. provided by developers or generated from another system, execution-based information and program analysis techniques can be integrated into the AutoCodeRover framework, section 4.4. For example, a statistical fault localization reference 35 tool can be used to reveal more relevant methods beyond those mentioned in the problem statement. The additionally revealed code context can thereby influence the set of retrieval APIs invoked in the context retrieval stage. Moreover, with test cases available, the patch generation agent can employ an additional patch validation step in its retry loop when crafting a patch. In the remainder of this section, we discuss in greater detail the components of AutoCodeRover and their design consideration.
Is there a new Lexus RX plug-in hybrid?
Context retrieval APIs. In the context retrieval stage, the basic components are a set of APIs which an LLM agent can use to gather relevant code context. Interfacing with LLM. For the LLM agent to invoke the context retrieval APIs, the description and expected output of them are presented to it as part of prompt. When the agent decides to invoke a set of retrieval APIs, it responds with a list of API call names and the corresponding arguments. These retrieval API requests are processed locally by parsing the local codebase of the project into abstract syntax tree, AST, and searching over it. Results of locally executing these APIs are returned to the agent, forming the code context. Comparing to other retrieval methods, an alternative for gathering relevant code context is to utilize information retrieval-based three-forward calculation of program dependencies from the hints. Reference 14 can be potentially used at this stage to further aid the retrieval. Figure 5. Stratified search with retrieval APIs for context gathering. Methods such as BM25 retrieval to find the relevant files in the project. The BM25 algorithm, reference 2627, ranks the set of files in the project based on their relevance to the words appeared in the issue description. In software engineering tasks, general retrieval methods such as BM25 retrieval can be less effective. Many content in the issue decryption, such as text describing the reproduction scenario, may not be directly relevant to the code in the project. Instead, our method utilizes...
Okay, we're 6 pages in. There's some interesting work with stratification and patch generation here. I'm not too interested. I think Sui agent basically is the same thing. I'm sure I'm wrong. I'm sure there's important differences, but in terms of like the hyper focus on the Sui bench light task, I think I would not be surprised if this was one of many similar approaches. Okay, cool. Yeah, I don't have like a ton of thoughts here. Perhaps this like AST aware stratified searching is good. It's a knowledge graph by any other name. And the system design is all right. I just wish that they had invested in a more Devon-like interface, but I can't blame them. Okay, cool. That is all I want to invest in for AutoCodeRover. Wasn't that interested in a paper anyway, but it's notable, and I've already done some background on all the other agents, competitors. So good to skip it and be familiar with what it does. The last paper we're going to do today is representation fine-tuning for language models. And that is also picked out by Rob. Really, I want to know who runs this account, because it has really good choices, unlike me. So we're gonna do ReFT now, and then I'll call it a night. So this one I expect to struggle with, but maybe people can talk us through it.
Laura, Hu et al., 2022, and variants such as Dora, Lu et al., 2024b, reduce the number of trainable parameters in learned weight updates by using low-rank approximations in place of full weight matrices during adapter training. QLORA, Detmers et al., 2023, further shows that full precision adapters can be trained on top of reduced precision models without sacrificing performance. Adapters are generally more efficient and effective than methods that introduce new model components, like prefix tuning, Li and Liang, 2021. A hallmark of current state-of-the-art PEFTs is that they modify weights rather than representations. However, much prior interpretability work has shown that representations encode rich semantic information, suggesting that editing representations might be a more powerful alternative to weight updates. In this paper, we pursue this hypothesis by developing and motivating representation fine-tuning, ReFT. Instead of adapting model weights, ReFT methods train interventions that *equal contribution manipulate a small fraction of model representations in order to steer model behaviors to solve downstream tasks at inference time. ReFT methods are drop-in replacements for weight-based PEFTs. This approach is inspired by recent work in LM interpretability that intervenes on representations to find faithful causal mechanisms, Geiger et al., 2023b, and to steer model behaviors at inference time, Turner et al., 2023, Li et al., 2024, and it can be seen as a generalization of the representation editing work of Wu et al., 2024a, Turner et al., reference 2023, and Zhou et al., reference 2023. See Appendix A for formal details on the relationships. We focus on a strong and highly efficient instance of the ReFT family that we call low-rank linear subspace ReFT, low ReFT. This is a parametrization of ReFT that intervenes on hidden representations in the linear subspace spanned by a low-rank projection matrix, building directly on the distributed alignment search, DOS, method of Geiger et al., 2023b, and Wu et al., reference 2023. We evaluate low ReFT on Llama family models and small-scale LMs against existing PEFTs on standard benchmarks from 4 domains: common sense reasoning, arithmetic reasoning, instruction following, and natural language understanding. Compared to LoRa, we find that low ReFT uses 10 times minus 50 times fewer parameters while achieving state-of-the-art performance for X out of Y number datasets. Fit 1. These findings indicate that ReFT methods are worthy of further exploration, as they may emerge as more efficient and effective alternatives to weight-based PEFTs. 2. Related work. Parameter-efficient fine-tuning methods, PEFTs. In contrast to full fine-tuning, PEFTs train only a fraction of the model's parameters to adapt it to downstream tasks. PEFTs can be classified into 3 main categories. 1. Adapter-based methods train additional modules, e.g. fully connected layers, on top of the frozen pre-trained model. Series adapters insert components between LM attention or MLP layers. Holsby et al., 2019, Pfeiffer et al., 2020, Wang et al., 2022, He et al., 2022b, Fu et al., 2021. While parallel adapters add modules alongside existing components, He et al. 2022a. Since adapters add new components that cannot be easily folded into existing model weights, they impose additional burden at inference time. 1, 2. Laura, Hu et al. 2022, and its recent variant Dora, Lu et al. 2024b use low-rank matrices to approximate additive weight updates during training and require no additional overhead during inference since the weight updates can be merged in the model. These are the strongest PEFTs currently. 2, 3. Prompt-based methods add randomly initialized soft tokens to the input, usually as a prefix, and train their embeddings while keeping the LM weights frozen. Li and Liang, 2021. The performance of these methods are often far from optimal compared to other PEFTs and come at the cost of significant inference overhead. A variant of this method where hidden layer activations are also tuned was introduced as a baseline in Hu et al. Reference 2022 with better performance. Instead of weight updates, REFT methods learn interventions to modify it.
This soft token business, I hear about them every now and then. Seems like a terrible idea.
Interventions to modify a small fraction of model representations. Representation editing. Recent work on activation steering and representation engineering shows that adding fixed steering vectors to the residual stream can enable a degree of control over pre-trained LM generations without the need for resource-intensive fine-tuning. Subramani et al. 2022. Turner et al. 2023. Zhou et al. 2023. Vogel 2024. For example, steering attention head outputs can increase performance on truthful QA. Li et al. 2024. Similarly, Wu et al. 2024a show that editing representations with a learned scaling and translation operation can approach, but not surpass, the performance of LoRa on a variety of models and tasks with far fewer learned parameters. The success of these methods affirms that representations induced by pre-trained LMs carry rich semantics. However, exploration of such methods has been sporadic and performance is suboptimal. Adapter-based PEFTs continue to be the state of the art and impose no additional inference burden. Interventional interpretability. Recent work in interpretability has used interventions under the framework of causal abstraction, Geiger et al. 2021, to test hypotheses about how LMs implement various behaviors. In particular, interventions on linear subspaces of representations have provided increasing evidence that human interpretable concepts are encoded linearly. This includes linguistic features such as gender and number. Rosri et al. 2022, Wang et al. 2023, Hanna et al. REFT. We now define a REFT family of methods. To do this, we first summarize the core motivation, which emerges from work on intervention-based model interpretability. We then show how this leads directly to low-rank linear subspace REFT, low ReFT. Finally, we generalize this to a family of REFT methods. To keep the presentation simple, we assume throughout that our target model is a transformer-based Baswani et al. 2017 LM that produces contextualized representations of sequences of tokens. Given a sequence of n input tokens x equals x1, xn, the model first embeds these into a list of representations h0 equals h01, h0n. Then n layers successively compute the jth list of hidden representations hj as a function of the previous list of hidden representations hj-1. Each hidden representation is a vector h element of Rd. The LM uses the final hidden representation.
I mean, this is a classic explanation of representation engineering. Nothing super novel here.
The final hidden representations HM to produce its predictions. In our experiments, we consider both autoregressive LMs and masked LMs. Devlin et al. 2019. An autoregressive LM predicts P xn plus 1 divides x1. Xn equals softmax WHM, while a masked LM predicts P xi divides x1. Xi minus 1, xi plus 1. Xn equals softmax WHM, where W is the learned matrix mapping from representations to logits over the vocabulary space. 3.1. Motivation. The linear representation hypothesis claims that concepts are encoded in linear subspaces of representations in neural networks. Early connectionist work on distributed neural representations was the first to propose this. Smolensky, 1986, Romelhart et al., 1986, McClellan et al., 1986, and recent empirical work has found evidence for this claim in neural models trained on natural language as well as other input distributions. Mikolov et al., 2013, Elhage et al., 2022, Park et al., 2023, Nanda et al., 2023, Gerner et al., 2023. In interpretability research, the framework of causal abstraction, Geiger et al., 2021, uses interchange interventions to causally establish the role of neural network components in implementing particular behaviors. The logic of the interchange intervention is as follows. If one fixes a representation to what it would have been given a counterfactual input, and this intervention consistently affects model output in the way predicted by our claims about the component producing that representation, then that component plays a causal role in the behavior being studied. To test whether a concept is encoded in a linear subspace of a representation, as claimed by the linear representation hypothesis, one may use a distributed interchange intervention, Geiger et al., 2023b. 3 let B be the hidden representation created at row I and column K when our model processes input B, and let S be the corresponding representation when that same model processes input X. A distributed interchange intervention.
I think that's like the key idea, so just paying special attention to this one.
Interchange intervention on B, given the counterfactual source representation S, is then defined as DII B S R equals B plus R, R's minus RB, 1, where R element of RR times D is a low-rank projection matrix with orthonormal rows. D is the representation dimensionality, and R is the dimensionality of the subspace we are intervening on. We learn the subspace R using distributed alignment search, DAS, which finds the subspace that maximizes the probability of the expected counterfactual output after intervention. DAS has been used to find linear representations in LMs of entity attributes. Huang et al., 2024, Linguistic Features, Aurora et al., 2024, Sentiment, Tigas et al., 2023, and Mathematical Reasoning, Wu et al., 2023, Lepori et al., 2023. However, experiments reveal that DAS is highly expressive and capable of finding causally efficacious subspaces even when a transformer LM has been randomly initialized and thus has not yet learned any task-specific representations. Wu et al., 2023, Aurora et.
Yeah, what is this distributed alignment search? I don't know what the fuck that is, but it seems powerful.
Aurora et al. 2024. While this has led to debate on whether DOS is faithful enough for interpretability purposes, McKellar et al. 2024. Wu et al. 2024c. DAS's expressivity suggests that it could serve as a powerful tool for controlling LM behaviors, in line with work on representation editing and controllable generation. Lee et al. 2024. Zhou et al. 2023. Therefore, we sought to use the distributed interchange intervention operation to make a new parameter-efficient method for adapting language models for downstream tasks. 3.2 Low-rank linear subspace ReFT, low ReFT, the formulation of DII and EQ. 1 immediately suggests a way to control model generations via interventions. The guiding intuition is that we can learn how to perform interventions that lead the model to accurately predict our task labels. The resulting method, low-rank linear subspace ReFT, low ReFT, is defined by the following variant of EQ. 1 phi low ReFT, H equals H plus R, WH plus B minus RH2. This is identical to EQ. 1, except we use a learned projected source Rs equals WH plus B. Intuitively, low ReFT edits the representation in the R-dimensional subspace spanned by the columns of R to take on the values obtained from our linear projection WH plus B. The learned parameters are phi equals R, W, B. As with DII, R element of RR times D is a low rank matrix with orthonormal rows where D is the hidden state dimensionality and R is less than or equal to D is the rank of the subspace. We further define a linear projection W element of RR times D and bias vector B element of RR. The parameters of the LM are frozen with trainable parameters phi. To simplify notation, we refer to the hidden representations produced by the LM on input X as HX and those by the intervened LM as H phi X. For single label classification tasks, we add a classification head H theta dot operator with parameters theta that takes the final layer representation at the first token, CLS, as input and outputs a distribution over classes. H has the learned parameters theta equals WO, BO, WD, BD. We learn the parameters of the head and those of the intervention function phi. We minimize the cross entropy loss of the target class Y given input X. Min phi theta minus log H theta Y divides H phi X phi. 3.3 The ReFT family of methods. It is straightforward to generalize the above to define a family of intervention-based representation fine-tuning methods. We first define a general notion of intervention, i.e. the modification of hidden representations during the model forward pass. Definition 3.1. An intervention I is a tuple phi P L that encapsulates a single inference time modification of the representations computed by a transformer-based LM. The three components of an intervention are the intervention function phi to RD right pointing arrow RD with learned parameters phi, a set of input positions P subset equal 1, n that the intervention is applied to, the layer L element of 1, m at which the intervention is applied. The intervention is applied immediately after the computation of HL and thus affects the representations computed in later layers HL plus 1. HM. Figure 2 provides a schematic overview of an intervention. A ReFT is then defined as a constrained set of non-overlapping interventions. Definition 3.2. A ReFT method is a set of F interventions I equals I1, IF. We enforce that for any two interventions IJ, IK element of I such that they operate on the same layer LJ equals LK, their intervention positions must be disjoint, i.e. PJ intersection PK equals empty set. The parameters phi1, phi f of all of the intervention functions are independent. ReFT is thus a generic framework encompassing interventions on hidden representations during the model forward pass. In Appendix A, we show how a variety of existing inference time intervention methods can be described within this framework. 4. Experiments. To evaluate low ReFT against existing PEFTs, we conduct experiments across 4 diverse NLP benchmarks covering more than 20 datasets. Our goal is to provide a rich picture of how low ReFT performs in different scenarios. Here is a brief overview of our benchmarks. Common sense reasoning, which contains 8 common sense reasoning datasets, including Boole Q, Clark et al., 2019, PIQA, Bisk et al.
Let's spend some time on this figure. Figure 2, left panel, this depicts an intervention I. The intervention function phi is applied to hidden representations at P and layer L. Yep. Specifically, the figure of the lowers at all layers. With the right panel depicts all hyperparameters tune. When not tying layer weights, we train a separate intervention between each position. 16 interventions with unique. Okay. Yep. Cool.
2020 SIQA. 2021
this paper list.
Natural language understanding, which contains 8 datasets from the GLUE benchmark, Wong et al. 2018, such as sentiment analysis and NAC. 2022. 4.1 hyperparameter configuration. N3, which set of layers L to intervene on. 4, whether or not to tie intervention parameters phi across different positions in the same layer. Following the definition of ReFT, we thus define the untied and tied variants of our low ReFT interventions. Additionally, when applying untied low ReFT to a prompt with length n where n less than p plus s, we set p left pointing arrow min, p n2, and s left pointing arrow min, s n2, and do not apply the truncated interventions in I untied. We also tune neural network training hyperparameters. Further details are provided in Appendix C. We graphically depict how an untied low ReFT intervenes on an example prompt in Fig. 2. Unlike previous works, Hu et al. 2022-2023, Lu et al. 2024b, where hyperparameter tuning may involve optimizing performance directly on test sets, we only tune our hyperparameters on development sets which do not contain any overlapping examples with the test sets of our tasks. We further describe hyperparameter tuning for each benchmark in Appendix C. 4.2 Common sense reasoning. We replicate the experimental setup in Hu et al. Reference 2023, and fine-tune Llama 17b and 13b on a combined dataset of 8 common sense reasoning tasks. COM Monsense 170K. We report scores on each task test set individually. We compare with PEFTs benchmarked in Hu et al. Reference 2023. We do not want to do hyperparameter. We report results in table. We only evaluate correctness on the final numeric or multiple choice answer. Hyperparameter tuning. We use the same hyperparameter settings as for the common sense reasoning benchmark with 12 ethics for training. Datasets. For more details on the datasets, see Appendix B.2. We use the same prompt template and hyperparameter settings as in the previous experiment. Results. We report results in Table 2. We find that low ReFT does not perform as well at arithmetic reasoning tasks compared to LoRa and adapters, but does outperform prefix tuning. Our results suggest that low ReFT may have more trouble on chain of thought reasoning than the single-step common sense reasoning tasks due to the length of generations, and greater length necessarily reduces the effect of the intervention and overall greater difficulty of the task. Our results show that low ReFT performs better with 13B model than 7B model, which suggests that low ReFT scales with model size. Overall, we know that the arithmetic reasoning results show a lot of variation, with no single method emerging as a clear winner across all of them. 4.4 Instruction following. Base LMs require instruction fine-tuning to follow human prompts. Yang et al. 2022. We follow the experimental setup in Wu et al. 2024a and fine-tune Llama 27B with ultra-feedback Kui et al. 2023. We compare against full parameter fine-tuning, LoRa and ReFT. We use Alpaca Eval version 1.0, Li et al. 2023, for evaluation, which computes win rate against text DaVinci 003 using GPT-4 as the annotator. We use the same prompt template as in Towery et al. Reference 2023. Datasets. We fine-tune Llama 27B with ultra-feedback. Ultra-feedback is high-quality instruction dataset where responses are generated via scoring a diverse set of model responses from a list of candidates, e.g. ChatGPT and Bard. The score is calculated as weighted score of its performing model to fine-tune on ultra-feedback. For hyperparameter tuning, we use Alpaca Eval version 125 model with highest in training validation accuracy to evaluate on the other held out half for testing accuracy. Hyperparameter tuning. We tune our hyperparameters for each task separately, which is standard for PDFTs. To avoid overfitting to random seeds, we hyperparameter tune our models with a constant seed and report average results over that and 4 additional unseen seeds. We describe hyperparameter tuning experiments in Appendix C. Results. We report results in Table 4. Low ReFT obtains comparable performance with PDFT methods on both model sizes when parameter matched with ReFT, the previous most parameter efficient PDFT for this task. Full results with standard deviation is in Table 10. 5 PyRef, a ReFT native Python library. To lower the cost of switching from PDFTs to ReFT, we release PyRef, a Python library made for training and sharing ReFTs. Our library is built on top of Python, Wu et al. 2024b, a library for performing and training activation interventions on arbitrary PyTorch models. We publish our library on Pippi. 5 any pre-trained LM available on Hugging Face is supported through PyRef for fine-tuning with ReFT methods, and fine-tuned models can be easily uploaded to Hugging Face. The following example shows steps to wrap a Llama 27B.
Wow, this is pretty based.
Model with a single intervention on the residual stream output of the 19th layer. IMPORT TOR CHIMPORT TRANSFORMERS from PYREFTIMPORT GET underscore REFT underscore MODEL REFTCONFIG LORCA USALL REPRESE underscore DIMENSION equal TOKENIZ underscore DATA underscore MODULE TOKEN model equals ReFT underscore model TOKENIZER equals tokenizer ARGS equals TRAINI 21A, Coped et al. 2023, as our proposed token rearrangement procedure to ensure efficient multi-codebook modeling. To evaluate speech editing, we manually crafted a first-of-its-kind, realistic, and challenging dataset named ReLEDIT. ReLEDIT consists of 310 real-world speech editing examples, with waveforms sourced from audiobooks, Zen et al. 2019, YouTube videos, Chen et al. 2021a, and Spotify podcasts, Clifton et al. 2020, and duration ranging from 5 seconds to 12 seconds. To create the target transcripts, the transcripts of the source speech are edited in such a way that the edited transcripts remain grammatically correct and are semantically coherent. The dataset is designed to cover a wide range of editing scenarios, including insertion, deletion, substitution, and multi-span editing, with the length of the edited text. So
we switched papers already at the end there, and I would say like probably the nicest part is just this bit here with the nice library that works with anything Hugging Face. Some of the results seem good, especially on the 7Bs. And I don't know what else I can comment on. I like that they also did on the 13Bs, and it seemed to do better there. Not by much. Like LoRa still has it beating on quite a few areas. So this is kind of incremental, probably cheaper. And what else can I say about it? Not much. I'm interested to understand the efficiency point of view. I feel like the results didn't like kind of blow me away, but maybe the amount of efficiency matters. I suspect it doesn't. I suspect there's a threshold, which LoRa fit just fine. Dora seems to be taking it over these days, but LoRa and Dora seem to be just fine. And even more efficient than that, do we care? No. Okay, cool. That is the ReFT paper. I don't think like this is particularly exciting in any sense. But I just wanted to knock this out for myself. And now you've been part of the process. Thank you for jumping along and spending a night with me.